Okay, well, good afternoon. Welcome to the second part of the Introduction to Python for Scientific Computing course. So today we're going to cover some further details of the Python language. We're going to talk a little bit more about Python data structures. We're going to talk about using functions and designing interfaces to address scientific problems. We're going to introduce classes and objects briefly towards the end of this talk. And I'll talk a bit about structuring a project, how to import modules, and a bit on writing tests, or at least writing code that hopefully will be less error prone. And with all of this in the context of scientific problems. So thank you to everyone who's fed back through the online system. I think people were quite keen to kind of see this applied to particular problems. So what I'm trying to do today is I'm going to focus very much on the problem of analysing data. So I'm going to look at all of the things we learned last week, but in the context of scientific computing and reading data. So I'll start with a 20-minute review of last week, and then I'll take some questions on that because we covered a lot of material quite quickly. So we'll go back over that again. I'll then present 10 minutes on using functions for reading data, and this is really going to be the aim of the hands-on session, to basically use these functions to import some data and analyse that. We'll then extend that idea using classes and objects, and the final hands-on session will build on the first one, and I'll finish with just the solutions to the hands-on. So last week we looked at basically using a Python command prompt as a way to develop code. So hopefully this week it will be easier to get started because you've all got Python working and we kind of ironed out any problems. And we talked about a range of different data types, floats and integers, and some of the problems with those. If we divide by integers, we get integers back, and how to be aware of those kind of problems. We talked about strings, lists, dictionaries, and we ended up by talking about NumPy and NumPy arrays. And the one thing I went to pains to emphasize, and hopefully it made sense, is that lists are not the same as NumPy arrays. The concept of an array that you multiply and use mathematically is a NumPy array. Lists themselves are kind of collections of data. So for most of data analysis that you do, we'll be using NumPy arrays. We talked about a range of different constructs, if statements, conditionals, iterators, and the definitions of various functions. And we talked about two main packages, NumPy and Matplotlib. Okay, so a recap on what a function is. Now, if you remember defining a variable, we use the syntax a is equal to 5, and that defines a to be the value 5. To define a function in Python, we use a def statement. What follows that is the name of the function. We then have some brackets where we specify the inputs for that function, and that can be one or more input variable. We use a colon here to specify the start of the function, and then the scope of the function, that is everything included in that function definition, is then specified in Python using an indent. Now the recommended indent is 4 spaces. The advice is not to use tabs, and whatever you do, don't mix spaces and tabs because you'll end up getting all sorts of very strange errors. So be consistent in what you do, ideally 4 spaces. Everything within the 4 spaces here is within the function. We use a doc string, which is basically just a string at the first line of the function, and that will be stored in the help and let people know what the function does. This is the main calculation of the function, multiplying the input by itself and storing it in an output variable, which is then returned to the user. And then we can call this function by passing in the value of a, which is 5 here, and we get 25 back. I gave some examples of functions, and although a function generally has to take some input, do some operation, return some output, actually you don't really need to do any of these things for it to be a valid function in Python. So divide function here is taking 2 inputs, dividing them and returning this output. But we could equally have a function that takes in 2 variables and actually returns nothing, does nothing. It would be a totally useless function. It's not a recommended thing to do, but it would actually not raise an error within Python. You can also have a function like this that actually takes in no variables and just returns something. And in this case, you'd call it using basically closed brackets. This would be useful if you had, say, a physical constant, like gravity, and you could just get that from a set value. You also don't have to use all the variables you pass in. So in this case, we're passing in a and b, and we're actually returning only b, only using the variable b. Equally, you can actually have variables that you don't need to specify, but are required for the calculation. And these are optional variables. To specify this, you give it a value that it will have if you don't override that. So for example, we could call line with specifying m and x, and c would automatically be 3 unless we override that and set it to what we want. And this is just an example of a slightly more involved function where we're solving a quadratic equation. We have a doc string that tells you what it does, and it gives you the solutions for that, which could be complex numbers if the root doesn't exist. We also talked about conditionals, which are basically just a way of deciding which branch of the code Python will run. So for example, if statement of A greater than B, if A is greater than B, it will print A, otherwise it will print both. So which bit of code gets run is determined by a logical condition. And you can use this to test type. I mentioned before this isn't the right way to test type, but just for example purposes. We're checking if type A is an integer, we add that to B, otherwise we print an error. And you also have this else-if syntax here, which is elif, which is slightly unusual if you're used to other languages. We talked about string manipulations. So strings in Python we can add together with other strings, and it concatenates them to form longer strings. We can also multiply them by integers to get a repeated string. We can access the individual elements of the string. Now the indexing starts from 0, so the third element is basically E here. So 0 is S, 1 is O, and so on. We can also take a range of elements, so from 0 to 4 would give you 0, 1, 2, 3, and some. There's also a whole range of inbuilt methods associated with a string, which we can basically use to make changes to that string. So we can do s.title, which will convert a string to a title case. We can capitalize, which capitalizes just the sentence. We can find particular characters, so x is not in the string, so it returns -1. If we ask it for something that is in the string, it will return O, and the location of that particular character. We can also do things like replace particular parts of the string. So in this case, we're replacing some with A, and we get a string. And I mentioned using Ipython. Now I think what I'll do is I'll cover basically how we run scripts and stuff in a second, but Ipython is useful because it allows you to basically have a more interactive experience. You can do tab and it will tell you which methods are available, which is quite useful for rapid code development. The next data type we talked about were lists. And lists can be a collection of any Python objects. So this one here is a string, it's an integer, a floating point number, and then another list itself. And then we can just retrieve elements from that list by basically using indexing. So we're getting the 0th element here, which would be another string. The third element here would give you the list, and then we can use the sub-indexing to get the first element of that list, and so on. Another way of moving through lists is using iterators. So we do for item in M, which is the list. And what that does is it will systematically step through the list, returning the elements of that list. Now I mentioned before that iterators are a more general concept than the type of looping you'd be used to in another language. In another language you normally loop through, say, a range of indices, so from I in 1, 2, 3, 4, 5. In Python, this for item in M, basically each time item is returned as an element from the list, and then you can do something with that item. So it's a kind of more general concept than going through the indices. However, you can still use this kind of idea of indices by setting up another list which has 4 values, using those 4 values to then access the elements of the list itself, and then, for example, if you want to make changes to them, you can add one. And I mentioned before, because of this idea that you're actually taking elements from a list inside this iterator, you can't make changes to them. So this I in this particular list is a temporary variable. It's effectively an element of that list that you have to save before you leave the loop, otherwise whatever you do to it will not be stored. The other data type I talked about are dictionaries, and these are really ways of storing slightly more involved collections of data. So this example here shows you one particular application, is you could store your strings, your integers, and your floats. And a dictionary you can think of like a list, but instead of accessing elements using numbers, we're accessing elements using strings. And those strings are looked up in a hash table, and they return the appropriate element. So for example, D of strings will give us red and blue. D of integers will give us 6, and so on. So it's another way of storing data that's particularly useful in particular cases. And again, we can iterate through these in the same way. So for key and D, and in this case, we're actually accessing elements of the dictionary using the key command. Now, in order to plotting, now Python is a general purpose language. It's not designed for scientific computing. So if you want to do plotting, you have to actually import 2 different libraries, Numpy and Matplotlib. There's also SciPy and Pandas. I might talk a bit more about SciPy next week, but and I'll also mention Pandas today, but really we'll focus on Numpy and Matplotlib, which will probably do most of the things you need to do in a kind of introductory context. So with Numpy, we import a module as import Numpy as MP, and this is a similar concept to includes, Fortran use module, RSource, Java import, I think, and in MATLAB having the code in the same path. the idea here is that we're actually importing Numpy, which is just a block of code. It's just another file full of code. Importing it as MP is just a shorthand, which means we can do MP dot and access everything in that block of code, every function, every object, etc. Now, Numpy arrays are basically a way of storing lists of lists and Python data in a mathematical form. So if you wanted a 3x3 matrix, you'd have to use a Numpy array, and you'd input values in this way. Now, Matplotlib is a way of doing similar plotting functionality to MATLAB. We import this using similar syntax. It's the pyplot submodule that's useful here. So generally, this is the only use you'll have of Matplotlib, and import it as PLT is again the convention. And the syntax again is plt.plot will access the plot function and plot the data, and then to show, you have to use the show command to actually make the figure appear. And again, with Ipython, you can press tab to see what's available. And there's lots of things: bar charts, histograms, etc. Okay, so here's a kind of complete example of plotting that I gave last week. So we import both Numpy and Matplotlib. We set up a linspace. So a linspace is just a function that returns from 0 to 2pi with 100 increments, equally spaced. We use Numpy sine and cosine functions that take that linspace, those 100 increments, and return y and z, and then we're plotting both of those. And notice by default, each plot command adds into the same plot, and then we show that at the end. So we get basically two plots on the same plot. This is a slightly different example that shows you the idea of using axes. So generally, anything you want to do with plotting in Matplotlib, it's very flexible, but it requires you to know a little bit more beneath the hood. So if anyone's interested in kind of specific plots or more details, come and see me during the hands-on session. But effectively, what we're doing now here is we're setting up two subplots. And to do that, we specify a figure handle, which hopefully you're used to if you use MATLAB or similar concept. But it's basically is kind of the handle for the figure, and this is a list of the different axes. So this is axis 0, this is axis 1. And then what we do is we use the methods of the axis. So axis 0.plot will plot onto axis 0. Axis 1.plot will plot onto axis 1. And then this just gives you an example of how you'd set the label. So you're actually setting a label to that particular axis, and then you show it at the end. And to be honest, there's very, very good documentation on Matplotlib for any type of plotting. They've got great examples. Anything you can imagine, you'll find an example you can kind of manipulate to your needs. So I gave this example this week, and we're going to go over this again today. This is how we'd load a comma-separated variable file. So this is a simple kind of output from Excel, basically just two columns separated by commas, and effectively we load that into the data. We extract, using this array slicing syntax, an x and y column. So the first column is got using this colon, comma 0, and the second is comma 1, and that gives us the x and y column, and then we just plot those two. And this is just a Matplotlib shorthand for plot a figure with dots and lines. Okay, so the idea is to build on these concepts in this session. So has anyone got any questions regarding this at this point? So one of the things, I was going to show you is basically how we run in Python on Windows a script. So for example, if I can minimize this because it's distracting. So if you write Python into kind of Windows Start menu, it'll open up an instance of Python. And this, I think you played around with last week, and this allows you to do the kind of inline calculations, the kind of playing around with that. And we also talked about Ipython. Now, if you want to access Ipython, I think a few people found that actually it's easier to open up a command prompt in Windows, and then you can actually type Ipython into the command prompt, and that opens up a version of Ipython. And this is, like I say, slightly more user-friendly. Now, typically what we'd do if we want to write scripts is we would write them in a notepad format. So, for example, if we want to do a script where we did, say, for I in like this. So I know the font's quite small, but the idea is then we could save this at some location. So I'm saving this on my desktop. I'll save this as, I don't know, test.py. So what this means is now, if I go to the desktop, I'm just doing cd as change directory, so I'm on my desktop now, and then I can type python test.py like that, and it will run the script in this way. So one of the ways to develop this, and I'll show you this today, is basically to have a script and then you run it in that form. And this is useful because I think, as you found last week, the syntax with the white spacing can be a bit of a nightmare, copying and pasting. So it is much easier to develop in a separate script and just run that. But at least for purposes of demonstration last week, we were copying and pasting. The other thing you can do, which is quite nice, is you can use Ipython with the I flag like this. And what that does is it runs the script like this, and then it drops to an interactive Python session, which means the variables that were defined in the script are still available. So I is now value 99, which is the last value. So that's useful if you have a bug in your script. You can then open up an interactive session and try to find what's wrong with that. Okay. So is there any other questions on any of those kind of basic concepts? So you'd like to see it with a bug? Or? Yeah? Oh, sorry, is it too small? Or? Oh, I see, sorry, yeah, okay. So you run the script with Ipython -i, which says drop to interactive session afterwards, which is quite useful for just debugging purposes. So for example, if we had some character that Python didn't recognize, and we run like that, what it will do is it will actually run to that point and it will tell you there's a mistake. So that's not defined, and then you can explore exactly what's wrong at that point, which is quite useful. Okay, fantastic. So, no other questions? Okay, so what I'm going to focus on today is a typical post-processing workflow. So, I imagine whatever branch of kind of research or science you're from, your workflow will involve some form of data, either it's experiments, numerical simulation, surveys, internet database, whatever else. You want to get that data. You want to import it into Python in some way, either as a Numpy array, a list of Numpy arrays, some organized dictionary. You want to then play around and look at various plots, analyze the data, see what you've actually got in terms of trends, and then the most promising of those outputs you'd save as a script and use this to generate something for publication. So this is a very typical use of Python. And what I want to talk about today is a way to generate a kind of more automated process that goes from data to figure with minimal user input. So this is to take the kind of tasks you typically do in writing a paper and generating the data for that and make them automated by a series of scripts. So this is very useful because it's easy to make changes when you're inevitably required by a reviewer to do that. It also gives you a clearer mapping from the data to output. And this is quite important in light of kind of open data and the requirement from the college that we have a much clearer kind of path between basically the data you've got and the results you present. It also allows you to help avoid bugs by breaking the actual data analysis down into a series of functions. So instead of one giant spreadsheet, you have a series of kind of steps towards your end result. And then what you can do is then, if your data is always the same, you can analyze it in a much quicker way. So I'm going to start with an example of a spreadsheet, and this is included in the file that I sent around. So effectively what we'd do is we'd save a particular spreadsheet. This is just an Excel spreadsheet here. And we'd save it as a comma-separated variable file. So in Excel you can just do file save as.csv, and it's a particular output type. And what that will give you is a file format that you can import. Now there are libraries to import directly from Excel, but generally it's more involved. And this is pretty much the easiest way. Now what you notice with this is that the actual numbers are stored correctly, but the actual column headers as well as the names don't appear. They're not a number. It's because Numpy arrays have to be one single data type. In this case, they're all floats. So what we can do is we can actually append names equals true. And what this does is it looks at the top column of the comma-separated variable file, and it uses that to define the names of the column. So this is quite nice because it allows you to access the data in the same way you access a dictionary. So you can do data, brackets, age keyword, and it will return the column of age data. The problem is we still haven't got the names here, again because they're not recognized by the float, recognized as float objects. So another option is to specify data types equals objects. And in doing this, what we do is we import our Our array basically is a series of strings or objects, and we have all of the data. The problem is now these floats are stored as strings, which means they're very inconvenient to mess around with. So my advice is, if this is the sort of data analysis you're interested in doing, something like Pandas is particularly good for this. Now, I personally don't use this myself, so I'm not going to talk too much, but it's quite an elegant framework. You basically read Pandas, using Pandas read control comma-separated variable file. It gives you the data in a kind of table format, but then you can do box plots, you can look at correlations, you can very quickly analyze that. So if you're going to be working with this sort of data, my advice is to investigate Pandas. What I'm going to talk about instead is how we look at data that is well suited to an application using Python. And this is data where, for example, we have 2D data stored in multiple files. We also have a header data, which is some metadata, and we basically want a series of functions that are going to read the header file and store those parameters. We want a list of the different files we have available, and we want a function that's going to read the data using the parameters from the header file and convert that into the correct format. So what we have here is basically 13 files which contain two-dimensional data, and it's stored basically as just a series of numbers. And what we want is a process that will take that data from all of those files and load whichever file we want directly into Python and allow us to plot that. So this is the aim of the hands-on session. We're effectively going to develop 3 functions: read header, get files, and read file. Starting from this particular script, and the idea is from that we should be able to analyze data in one of 3 formats. Now, in terms of reading the header, the idea here is we're going to read it as a dictionary. So the header format is basically just a table here of, a file here with just these keyword and number. And what we're going to do is we're going to loop through that. We're going to split the string, which is each of the lines, and we're going to store them inside a dictionary. And in order to actually store this data, because it's a mix of integers and floating points, you can use integers and floats. Don't worry too much about this. You've got the notes, and also we'll be here to help you with this. But this is just to give you an idea of one way of doing this. And there is no unique way to do this. The next task is to get all files in a folder. And if you remember last week in the hands-on session, we included an example where we generated a range of different file numbers from 0 to 9. Now, the problem with this is because our file names are actually in the format 5 digits, and they go above 10, this particular approach won't work. So actually a better way to do this is using file name thissyntax.format. And this is incredibly useful. What it does is it generates a sequential set of files. So if you're generating videos from your data, or you're actually analyzing data, this particular syntax is extremely useful for storing data in a kind of sane and very readable format. You can also use the module global to look at the details in a file. And this is a module we haven't talked about. I've only really used it for this, and it will give you, based on a particular string, all of the files with those parameters. Now, for the hands-on exercise, we've actually got data in 3 different formats. We've got column format, which is basically just a series of numbers, like a comma-separated variable with 1 column. We've got binary format, which you basically won't be able to look at because it's stored as zeros and ones, but you can read using a Python function. And we've also got text format, which is actually an example output from an existing CFD code, just to give you an idea of one of the types of format you might approach. But if anyone has particular data from their own research they'd like to look at, then please feel free to ignore this and actually work on developing these same ideas for your own data. So the reading of the 2D data as a column, we're basically going to use gen from text, which is a Numpy helper function that lets us do that. And we have to reshape it. Now, if you look at the header file, we can see that this 2-dimensional field is basically 84 by 50. So we're going to reshape it in this format, and this will give us the data in the correct format. If it's binary data, we can use a Numpy function called fromFile, which we open up using the read binary flag here. So that's saying read only, and it's in binary format. We have to tell it the data type is all double precision numbers. And you'd have to know this in advance, and this would be something that would be either included in the header file or you'd know from having written the data. And again, we reshape it. And the third format is actually copied from OpenFOAM, which is basically just a kind of mock-up, and the actual header is inside the file itself as text. And we have these kind of keywords that allow you to specify what the data corresponds to. Okay, so I mean that's quite a lot of information. Really what I want you to basically do is to think of ways to actually read this data. So you've got the data in the 3 files, and you have to develop 3 functions here that take in the folder name and a header, the folder name and the file name, and basically the actual file name, and from that actually read the data and plot it. So we've got our two tutors here, Isaac and Edu, who've kindly agreed to come and give their time to help you out with this problem. Fantastic. Okay, so what I'm going to try to do now is show you basically how to solve this problem. So how to write these three functions to analyze data. Now, what you probably found is this is quite frustrating. There's lots of weird quirks, for example, relative paths to where the files are, you know, how to design a kind of general purpose way to read files. This is pretty much, you know, a research problem. So it's not a simple thing to do, and this is kind of chosen so you've got an example that hopefully will actually directly be relevant. But as a result, it involves lots of weird quirks of file systems and, you know, being in the right directory and things like that. So what I'm going to do is I'm going to show you how to basically write this function. So what I'll do is I'll open up at the same time a terminal. Oops, sorry. Okay, hopefully that's actually, so this is better on this side. So what I'm going to do is got a terminal here, and we've got a file here. So this is probably the easiest way to develop code. Now, we've talked before about how to use Ipython to actually, you know, try out things, and you can still do that, but my advice is if you start getting beyond a certain size of file, it's much more convenient to have it basically stored in a text file and then to actually run that. So what we do is we have to go to the directory where the text file's stored. So for me, that's documents, presentations, Python teaching, week 2, 2D data. And then we can double check using ls the contents of that directory, and we see solutions, which is the name of the script that I've saved in this. So what I can now do is I can do Python solutions.py. And we see here it's running the file and it's giving us an error message here. So this is the way I'd recommend actually developing files. It's basically having both a text file and a terminal open at the same time, and just keep running it and see what errors it comes up with, and then fix the errors, and then move on. So it's actually quite a nice way to run. So what it's telling us is, for f in files, none type object is not iterable. The reason we're getting that is because our files, which is returned here, so the pass statement here for get files returns nothing, it does nothing, which means that we're actually returning, by default, files is a none type. It doesn't know how to deal with that. So we're trying to iterate through a none type, and it raises this error. So we can fix that straight away by basically saying return files, where we define files to basically be an empty list. And already that removes the error. So what it's doing is it's basically just returning an empty list here. So in order to actually develop this function, I'm going to put a print statement afterwards. So this print statement is just going to tell us the contents of files. So we run Python, and it's telling us here that it's an empty list here. So what we want to do is develop a function that fills that list with the files in our folder that we want to look at. So in order to develop this, what I'm going to do is I'm going to open up an Ipython terminal to just play around. And I'm going to import global. Now, I mentioned this was one way to do this. There are a few different ways to basically look at the data, but global is potentially one of the easiest, because we can use glob.glob. And then we can basically, I'm going to look at column data here. And we want file name. And if we do tab, it tells us basically the format of the file name. And this star here basically is like a wild card. It basically says, take everything with file name and any other characters following that. So if I do glob.glob, it will tell me there's an error scanning because I had basically the wrong quote. So you see now what we're getting is it's telling me all of the files inside that folder, which is nice. So now I can save that to a variable, files, like that. So files is now a list. Now what you notice is this list is in the wrong order. Ideally we want them ordered from 0 to 1. So in order to do that, if you do tab, you can see there's actually the sort method for our files list here. So this is kind of one of the examples of one of the annoying things you'll have to work around. You've got your data in some format. You have to basically load that data and work out how to get it in the format that's most useful to your research. So we've been playing around with Ipython. We want to copy that now into our script. You can actually use the history statement, and it will tell you all of the different commands you've run before. So what I can do is I can copy this to define files here. my copy file sort. Oh. File sort. And then we're returning files. So now we've got a function here that's going to basically, from a directory, get the files that we want. So we exit that, we try running our Python again. It's telling us that glob's not defined, which means we need to import glob at the top. So I'm deliberately doing this in a way that shows you, how many mistakes you can make and how you can keep kind of responding to those mistakes. And it's one of the nice things about Python is you can almost do this step by step, checking your output every time. So you now see we're getting all of the files here. The problem is I've hardwired this here, which means that it would only work for column. It wouldn't work if I had a different folder name and file name. So actually, to make this a general function, what I need to do is I actually need to replace column here with folder name. And I need to replace file name here with the variable file name. And to the end of that, I'm going to add the wildcard search star. And we run that again, and we get exactly the same solution. But what that means now is if I change here, column, say, to binary, it now gets all of the values for binary. So it's basically the function doing what we want. Now the next function we want to look at is one that basically reads the header. So we'll delete print files because now we've got get files working. And we want to print the output of header here. It would help if I spell that correctly. Okay, so it's now telling us okay, so what we're going to do is we're going to stick in header variable, and now we want our header to be a dictionary. The reason we're using a dictionary here is partly just to show you one possible application of dictionary, but also because it's quite an elegant format here to read the dictionary. And you can see we're printing here the empty dictionary character that we've just specified here. So now what we want to do is we want to actually we want to open our header file, and we want to load the data into this header dictionary. So the way we open a file is to do f equals open header name. Now what this statement here basically says is open the file header name. The way Python works is this open statement effectively gives you a pointer to the open file. You can then use that pointer to read data from the file. So let me show you an example in Ipython. See, header name is not defined, so we have to do column header like this. So f dot has all of these associated methods. For example, we can read lines, we can write to it. It's basically a pointer to a file that lets us play around and manipulate with that file. So what we want from this is we want to use an iterator to go through the lines in the file. So for line in f dot read lines, and we're going to print L. So we exit this, and we run our solution again. And what you see now is it's actually looping through the file, and it's printing each of the different lines in that file. So that's good. Now what we want to do is we want to actually split these lines up. So we want to split the lines using the space between the two columns. So if we do that, you can see now what we're getting is two columns. We've got on the left here, the first value is the variable name. The left one here is the number. Now the problem is we've also got this weird /n thing. Now this is a new line character. When you have a text file, each new line is specified by this /n. So when you try to read it with Python, you get this. What that means is we actually need to strip this out. Like that. And then we can run it again, and we can see now it's gone. Okay, so brilliant. So what we've got is a mixture here of basically integers and floats, but they're stored here as strings. Now what we want to do is we want to convert them to integers and floats, so we can use them in our calculation. So what we're going to do is we're going to save the output of this as key value is equal to that. So what this syntax here means is basically take the first column and save it in key, take the second column and save it in value. And notice, the actual output functions doesn't need to have brackets around it. You just specify them as a kind of comma-separated list. And if we print that, again, we get the same set of values. Okay, so now what we want to do is we want to convert, we basically want to store them in our dictionary. So header, brackets, key, is equal to value. So what that means is store in the value, in the header, with the name, key, set that to that value there. And we can see now our dictionary that we're returning is actually returning the right thing. So we're actually getting nx with this colon, has a value at 84, and so on. But we want to convert that now to the correct format. So in other words, we basically just change it from a string to an integer like this. And that's raising an error now. It's basically telling us that the floating point number, 1560, can't be converted to an integer. And this is where we can start to use Python's error handling. And this is actually a recommended way to handle something like this. You're basically trying to convert it to an integer. If that's not possible, let's fall back and try to convert it to something more general, a float. So what we do is we try an integer. If it fails, with the exception, so we say except, value error, then try to do something else. Sorry, float. Okay, brilliant. So now we're getting a dictionary back, and we can see the numbers are in the correct format. These are floats, these are integers, and everything's in the correct format. Okay, so we've got a function now that's reading our header. We've got a function that's getting our files. The last thing we need is basically to read the contents of the file. And this actually turns out to be the easiest bit. For the column format, we basically just do gen from text. And the reason this is the easiest bit is because Numpy actually provides the ability to do that. Now it's telling us that Numpy isn't imported. So hopefully you can see by me kind of making mistakes like this that actually this is the easiest way to develop code. You just keep trying things, and then you address the error, then you try things. And you have a kind of overall structure in mind of the type of functions that you want to develop. And you know what you want to put in and what you want to get back. So this kind of you start your project by kind of thinking about what you want to achieve, and then you kind of work through in this way. And with a bit of luck, this will work. And it's moving through the files, and you can see it's plotting. So it's converting the kind of list of data into a 2D array. And it moves through and plots each of the different values. Okay, so hopefully that made sense. Now one thing you notice about all of this is we're actually defining the functional interface. That is, a kind of contract with the user. It's saying if you give me, the file name or the folder name, what I'll give you back is, say, the list of files or the contents of that file. And this kind of idea of functional interface is quite important in designing your code. This idea that you kind of got a contract with your user that doesn't change. And the reason this is particularly important is because it means all three exercises actually return the same data but from different files. And it means that we could use exactly the same top-level code for all three files. So you notice that the binary, column data, or text data, we could read all of those without changing one single keyword. And what's nice is this hides from the user, which could be someone else you give your code to, but also you in a year's time when you've forgotten what you were doing before. All you have to do is say read data, point it at the file, and it will actually load that data for you. You don't have to care about the underlying format, provided that hasn't changed. Or if it has changed, all you have to do is write just that function, and then the rest of your code works. So it means that you've kind of separated out the functionality. And this kind of idea is actually central to versioning control. So if you go from version 1 to 1.1, that means the interface typically has stayed the same. If you've got a major version number change from, say, 1.1 to 2, the interface is no longer the same, no longer backwards compatible. So it's kind of, this is, one of the fundamental principles of software design. And you take this principle in developing what's called test-driven development. So the idea of this is that you basically decide beforehand the sort of function you're going to design. You actually specify tests for the function, and you see that it works. So this is a similar concept to what you saw before with me iterating. So we open up a new file here. We save that as test.py. The formatting is messed up. So this is again one of the things that's quite annoying about having the syntax based on spaces. Okay, so now if we run that, what it will tell you. Okay, so it's telling us that the two tests run correctly. These two tests are basically testing that if we pass in a float of 2, we get back 4 as a float. If we pass in an integer of 2, we get back 4 as an integer. Now, If we specify that to be equal to, say, a different value, 3, what that will do is it will tell you that the test has failed, and it will tell you which test has failed. Assert here is a keyword that basically says, if this isn't true, raise an error. So you're almost in advance saying, I want a function that does this. If it doesn't, raise the error straight away. And this is very, very useful. If you want to develop a function and ensure it definitely works exactly as expected, you set up a series of tests, you develop your function, and then you're testing it. And the idea is you build up this bank of tests that never change, which means you can run these every night or whenever you make a change to your code to make sure the function still does what you expect. And actually this is the kind of philosophy behind test-driven development. And this is what's used in pretty much most commercial software development companies. The idea would be that you would actually, from your boss, you'd get told to develop some function. So in this case, let's say we've got this function here that's ridiculous. It tells you that, you know, if you pass in 2 as a float, I want 8 back. If you pass in 2 as an integer, I want 4 back. And we start with basically just some empty function here, and we say what function will satisfy that requirement. So if we run that, obviously both tests fail. It's not working. So what we need to do is we need to develop something in this test that will work. So let's say we try try return a squared like this. What we can see is only one of the tests is failing now. So the first test actually passes, the 2 equals 4, but the second test isn't. So we could try cube. And again, what that will tell us is, again, one of the tests has failed. So this means that our function has to be more complicated than what we've tried already. So we could try something like if type of A is int, return squared, else cube, like that. We run the test, and it tells us both tests run correctly. So the idea here is you've written the test first, and then you basically write the code to satisfy this, even if the code itself is totally stupid. Okay, so this is just the same idea, and you just keep developing. Okay, so the last thing I want to cover briefly, and I don't think we're going to get time to do the last hands-on exercise, but I'd like to just cover this as a kind of introduction. Next week is classes in Python. So the idea of this is a class is just another way of organizing data. So for example, the syntax here is very similar to what we saw with the function definition. You say class to tell it you're developing class, the name of the class here, open and close brackets, and a colon, and then the 4 spaces of indent, and then you can define variables inside your class. Now a class is just a way of kind of collecting together things with a similar concept. So one example of this would be, say, if you had a class person, you'd collect all of the things associated with a person for that class. So for example, their age, their name, etc. And it's a way to organize data. And you can use this as a kind of static container. So we've already got used to this dot type notation. So let's say we design. So we've got my class here, and you look at my class dot, and we know we have a and I associated with that class. What you can also do is you can create an instance of my class here. So you can say my class, and C is now an instance of the class, and that has again the same variables I and A associated with it. Now, for those of you who know object-oriented programming, this instance of it is called an object. So the instance of your class is called an object. In Python, there's no protection for private variables. So actually you can do C.A, and you can actually redefine that value. So there's no protection of those variables, which means you can actually redefine the variables in the class. Now the reason why classes are important, why they go beyond things like dictionaries and lists that we've talked about before, is because they can start to include functions. And the idea of these functions is they will actually act, they will collect together kind of functions with similar purposes. So in this example, we've got the square function. We've seen quite a few times already. We can build that into my class like this. Problem is, 1 second. Okay, fantastic. So in my class now, and we now have I'm having a problem with the white spacing. Okay, brilliant. So my class dot A. Oh, I see. Sorry. So yeah. So this is why beyond a certain size you should certainly work with a notepad and actually run that, because copying and pasting it is not easy to do. But so we've got this class here, and hopefully now my class contains square. Brilliant. So now we can pass in, say, 4 to square. It'll tell us, basically it won't let us do that. So we actually have to create an instance of the class in order to use the square function. So a.a and a.i are still defined. And we can do a.square. And it allows us to then apply a square operation to a function. So it's a way of collecting together both values and functions. And where this becomes useful is if you remember something like strings. Now with strings it was quite useful to define, say, a string and then have all of these functions that can adjust the string associated with it. So Python provides us with all of these ways of taking the string and getting the title of that, so we get it with a capital. And it's good to design code that actually allows you to not only have data variables but methods that actually act on those data variables that are most appropriate for manipulating them. So in order to do that, what we do is we'd actually rewrite our functions to operate on the internal variables themselves. Now what you see in the functions of a class is you always have this self keyword here. And that's basically in the same way that we saw with s.title, you can think of as being title brackets s. This is kind of, actually the reason why that's the case. So this is saying, if I'm going to do a square function, the variable I'm going to pass in is my class itself. My class refers to itself as self inside. And then we're taking the value a from class and squaring it. And this would be useful, for example, in the context of this person example, where you'd have an age and you'd have a name, and then you'd actually have a function that specifies your age at your next birthday. And that is only really relevant to that particular person. What that does is it returns their age and adds 1 to it. So it will tell you the age plus 1 for that person, for something about that person. Exactly, yeah. So if you did, so within this context, you'd self the dot name, and that would give you basically John Doe internally.
Rather than using self, if we look at the square one, get square bracket, we do not specify my class as it's type there. Would that not give you the same answer?
You mean instead of self?
Yeah.
Oh, I see. Yeah. Good question. That works? So I mean, if you use things like C++, this would be the this keyword. I mean, there's this kind of concept of, I think that would probably work for a static version of the class, but the idea is what you're doing is you're creating an instance of that class. So for that, I think self would be the kind of reliable way of doing that. So when you create an instance of a class, self refers to that instance. My class is like a static declaration. So my class is like a kind of always the same thing. Whereas when you create an instance of that, that's then that can be varied, and then that's when self becomes. Yeah.
So because there are like class methods, so the variables that are declared inside that class are called attributes, and the functions that belong to that class or declared inside the class, they are called methods, like the jargon. So you can have in Python a class or object or instance variables. That means that they can be accessed if they are instances or not. So the way it's defined like this, in the example, you have a and I that have been defined outside any function of the class, so they are class variables. But the way a square was defined as with self as the first parameter, that means that it's not a class method, it's a method of the instance. If you remove self, for instance, you can remove self from there. Then you cannot call a, but it will become a...
You mean if I delete self from here, yeah?
Yeah, if you remove self from there, then it becomes a I think it's too much because it is, yeah, that's the danger of.
Yeah, no.
Yeah,
So
sorry.
part of the reason I want to introduce this is because everything in Python is an object. So we've already been playing around with objects. When you do file.read or you do string.capitalize, they are all objects. You are using methods of objects. I'm trying to at least give an introduction, but it ends up with getting into kind of lots of quite involved concepts.
I think the best way would be to define, to say what is the constructor and then define a
Yeah.
cell, A and
Okay.
cell.
Let me get to so with this, if we do C, so we've created an instance of the class C here, and C has A, and C has I associated with it. If we call C.square like this, it will square the value of A. But basically, what we did before is we're statically defining those variables. Actually, what you're going to want to do is define a class where those variables aren't known beforehand. So you define some function that sets the variable that's passed in to the function. So the idea here is we've got this class here, and we would So if we do my class.square, okay. So for some reason, I don't know why, this seemed to work last week, but for some reason this week, all of the white spacing has just totally failed in all of the examples. Okay, so let's say we try the syntax of Ipython test here -I. So it's basically running the script and it's getting to the end of it, which means my class is now defined.
I think it should take a bit.
Yeah, so. Okay, so my class is defined here, and we want to call the square function. It's going to tell us that actually it can't square because A hasn't been defined. So what we would need to do is set value first to be 5, for example. Sorry. Absolute nightmare. Yeah, that should be fine, right? Yeah, no, you're right. You're right. It's not letting me do that. Okay, fine, forget that. So I wanted to build up to the idea of a constructor for this. I'm having a nightmare with the index. So basically, the problem with that is, you could write a function that lets you set the value inside your class, and then you could use that where the square then applies to that value. Actually, Python provides inbuilt syntax for doing that, and it's called a constructor. The idea is that when you use this syntax, this is what's called by default when you create an instance of your class. So let's take this example of the class here. Copy it into a file. There are no protected variables. The way of protecting variables would be underscores before. This is just the definition of a constructor. In it, it's just the definition of a constructor in Python.
Once the value has been defined, then you can access A and int.
Yes. So actually, if you look at if we looked at my class dot, it's only got square defined. There's actually no A defined by default because it doesn't know that A is going to be defined later on. So if we did see my class brackets 4, now C, which is an instance of my class, actually has A defined now. And you can do things like C.B is equal to like 6, like that, and then has got B defined. But the idea of this would be that you would then call square, and it would square the value of A you've set, if that makes sense. So where this makes sense would be if you designed a class number, for example, where you would specify the value of the number, and then that number would also have a whole set of associated methods with it that could square that number, could cube that number, could provide basically mathematical functionality associated with the number you've set up. So hopefully this gives you at least an idea of how this could be useful in the context of building up kind of a set of functionality in a class that's associated with that type of object. So the reason why this is important for the problems you've just seen is actually now what we can do is we can design a class called postprocess. That class called postprocess can take in initially a folder name, a file name, and a header name. It specifies everything you need to know about your entire data structure. It has a series of functions that operate and do exactly what we did in the last hands-on session. So that's get the header file, get the files, open all of that. So it's basically a kind of collection of code purely associated with post-processing. And we can go a bit further with that, and we can actually then in the constructor of our post-processing class call the function to read the header and the function to get the files. And what that means is actually this post-processing class then has a list of all of the files. It has all of the header information. It has everything we need to post-process the data we've got associated with it. And that simplifies our code. It means that if you actually write everything in the class in that format, our code simply becomes post-process instance. So we actually instantiating our class post-process with a binary, the folder name, the header name, and the file name. And then we can do for a file in pp.files, loop through and actually plot. So it reduces the previous example down to this. So I know this hasn't been a great explanation, partly because it's been a nightmare to paste in the white space, but hopefully you can appreciate that actually this is quite an elegant way of actually building up a kind of post-processing object. But what's more importantly is a lot of this is already happening behind the scenes in Python. So hopefully it gives you some idea as well about what's happening when you're doing dot reshape, for example. This is a method that's actually reshaping the data. So this data here is a Numpy array. Numpy arrays have associated methods that can manipulate that data. So dot reshape here is reshaping that data into a 84 by 50 array from just a column of data. So this idea of kind of building methods associated with data is kind of central to Python. So we had another hands-on session, but I think we're kind of behind time on that. So the one thing I wanted to cover just last of all is we've gone beyond scripts. We talked briefly about classes and grouping methods together. Another thing you can do is you can actually basically, if we save all of the code we've written in a separate file, so in this case, let's say we've got a 2D data, and we save our post-processing library code, which here is basically the constructor that I just showed you, the file, the header data which we had before, the get files, and a few other things to get the records. We save all of that into a post-processing file, and as long as that's in the same directory, what that means is we can actually go to that directory. So let's see 2D data. We can open an Ipython, and we can say import proclib as ppl, and in this ppl dot, so that's got, because it's this file here, it's got numpy, global, and then postprocess as available methods. So what we can do is we can instantiate postprocess. We specify that we want the binary folder, the header data, and say the file name. We're going to create an instance of that. Yes, you're right, thank you. Brilliant. So now we've got PP, and now this has a whole set of associated methods that we've built up. So these are methods that, for example, we look at files, it's got all the files in there. We look at header, it's got all of the header information in there. So this is kind of giving you an idea of how you can actually start to build up this kind of library of tools, put them in a separate folder, and actually then use them to access data in whatever format you've got it. And you can also change the folder name and then rerun the analysis. So we could say change folder name. No, I'm not going to do that. That's a bad idea. No, maybe that'll work. So if we change that to column. Sorry, I've just done something stupid. That's fine. So just give you an idea of how you organize the data. And then that allows you to basically read the data in this format. And the last thing I wanted to show you is basically just one way we could use this. So basically this slider using PPL is just a script that basically takes the post-processing object and just loads data from it when you pass in a number. And what's nice is using Matplotlib widgets that allow you to design a slider. You can design a kind of rudimentary graphical user interface that basically lets you analyze your data, and based on where the slider is, load that particular data file. So in other words, I've not done anything more than just use the kind of functions we've already written I showed you in the first part, and just use this kind of slider idea where you're basically asking for a particular record, and then that loads the file. And this also comes back to this idea of functional interface. So because you've written your functions in a way that always return the same output, it means that actually you can then analyze any different data file by just changing a single keyword, and then you can use exactly the same interface, the same slider, and over time as you build up a kind of more complicated interface to the data, it will all work regardless of the particular format of the underlying data. I'm not going to talk about this because it's more involved, but basically you can use, for people who've done object-oriented, you can use inheritance to kind of actually simplify this. You can use your post-process class and actually just inherit and overwrite the read files, and from that you can actually then get basically on one page the entire analysis of all three different files. Okay, so I mean, hopefully this has been useful. I've talked more on Python data structures. I've talked about functions and design of interfaces. I've given an introduction to classes and objects. I've talked about structuring a project and how to kind of build up a set of code, import it as modules, and basically how to not only run scripts, but also actually the more kind of formal way of actually writing tests to define beforehand the functionality, which is kind of the recommended way of developing code. And this has all been in the context of usage for scientific data analysis. So I'm happy to stay around if anyone's got any questions. Obviously feel free to do the hands-on session, and if you've got any questions, let me know, and I'll send solutions to those. Anyway.